Hi guys, I'm going to work out these problems from practice problems 2.2.2 where we had radical functions and rational functions. So let's go ahead and do this one right here, number 1. And the way we did it in class was remembering that this right here, the radicand, x minus 2, has to be greater than or equal to 0 for radical functions, or else it becomes an imaginary number, and then we just solve. So x is greater than 2. So to show the domain of this, it would be x, that x has to be greater than or equal to 2. Okay, now the range of radical functions. Let's go ahead and draw a radical parent function. It's a sideways parabola. It's half of sideways parabola, and it's going to look like that. And so the range is going to start from kind of that vertex right there. And so nothing, no left or right movement happened. No, actually it did. It moved right too, but no up or down movement happened. So range is affected by the up or the down movement. And it would have to be some kind of number that is either added or subtracted to that. It also gets affected by reflections. There's no reflections, and you see that this right here doesn't have a multiplier. And so it's just going to be y is greater than or equal to 0. And so I could go ahead and put that in. So y, just that y is greater than or equal to 0. To put this into set builder, this is set builder notation. To put it into interval notation, it would be, no, not that. It would be 2 comma positive infinity, and that would be 0 comma positive infinity. And there was another way in the textbook that they had just using brackets, and I think that's a European way because they don't use parentheses, they only use brackets. You can put a bracket here and a bracket that looks like that, and that just means it gets it doesn't include the positive infinity. Here, 0, something like that. Okay, good job, guys. Let's do number 2. Let's do number 2. Once again, I'm going to take that radicand, set it greater than or equal to 0, and then solve. So x is greater than or equal to positive 2. 2 divided by 3. My domain is going to be x such that x is greater than or equal to 2/3. If I write that as a interval notation, it is going to be starts at 2/3 and goes to positive infinity. If I write that in the other interval notation, 2/3 and then positive infinity and this awkward looking bracket. Okay, the range, once again, is going to be y is greater than or equal to 0. So that means my range y such that y is greater than or equal to 0. And this makes sense. I mean, if you think about a radical function, inside the radical, whatever the radical is, well, this is a square root. If it was a cube root, then it would actually work. But the domain of all of this, the radicand, has to be greater than or equal to 0. And then that means the output, the product of that, has to be greater than or equal to 0. Put this in range. And so we have 0 and positive infinity. Once again, represented in the other way. So we have 0, positive infinity, and that bracket right there. And you can actually take this bracket and write it in here. I've seen that being done. You can take that entire bracket right there and then put it into your set builder notation. Okay, now we're getting a little bit, so let's look at number 3. This one is interesting because it's not as simple as 1 or 2. What I'm going to do inside of this, no, I don't really need to do that, but I mean, to see, let's go ahead and take it. I'm going to rewrite this. Okay, and then I'm going to go ahead and take that radicand out. That radicand has to be greater than or equal to 0. Negative 4x. So greater than or equal to negative 2. And then divide by negative 4. X. This becomes U-turn 1/2. Okay. So notice what happened. This is very important to figure out as we get into transformations. You see this? Let me choose this. You see this negative 4 in front of the x? Okay, look what that did to the domain, or what could be the domain. It completely kind of flipped it. What I can do is I'm going to take a negative 4 out of the radical, of the radicand, I mean, and it becomes x minus 1/2. Okay, remember this has to be in the form, in that form later on when we transform and figure out horizontal and vertical stretches and compressions. Okay, because this negative 4 needs to multiply the entire x. The x was moved right 1/2, and then it was multiplied by negative 4. Okay, so just remember that that needs to be done. So based on this, this implies that domain x such that x is less than or equal to 1/2. Write it in set builder notation. Negative infinity to 1/2. The other set builder notation, it's going to look like this. Negative infinity and 1/2. Okay, let's look at what happens to the range. And in class, I wanted you to do this algebraically. So square root of 2 minus 4x has to be greater than or equal to 0. We'll change the color for the range. But let's look at what else is being done. This 1 is being added to it. So all you do is take 2 minus 4x, add 1 to both sides. And so you have the entire function now being greater than or equal to 1. The entire function is the range. It's the output. Okay? So therefore, y has to be greater than or equal to 1. And then let's go ahead and write this. Y such that y has to be greater than or equal to 1. And then the range, which is 1, positive infinity. And then the other notation, 1, infinity, and this funny looking bracket. Okay? Good job, guys. Okay, number 4. take a look at this. Let's look at the radicand. Remember, the domain is set by that radicand. So it's going to be 2x plus 1 has to be greater than or equal to 0. You can solve. -1, x has to be greater than or equal to -1/2. Okay, let's go ahead and write our step builder notation. X has to be greater than or equal to -1/2. Let's go ahead and write it in interval notation. -1/2 starts at -1/2 and continues on to infinity. The other one, -1/2, positive infinity, and that funky little bracket. Now let's go ahead and figure out the range. Once again, the range is defined by the entire function, not just the radicand. And so I'm going to rewrite that entire radical has to be greater than or equal to 0. Let's see what happened to it. Okay. Well, first you see that -1 is being multiplied right here. Right here you see that -1 is being multiplied to this radical. So I'm going to go ahead and change that. Okay. I'm going to multiply -1 times the radical. And what I do to one side, I have to do to the other. 0. Okay. Times -1. When you do that, it also changes the inequality, because when you multiply, it's a U-turn. So negative square root of 2x plus 1 less than or equal to -1. And then notice what happens. 3 is being added. Okay, so I'm going to go ahead and add 3. I have to do it to both sides. Oh, where did I get this? Sorry, -1. It's just 0. Add 3. So I have what it looks like an exact copy of the output. So we have 3 minus square root of 2x plus 1 less than or equal to 3. So that's y is less than or equal to 3. So therefore, we have the range y such that y is less than or equal to 3. Let's go ahead and write that in interval notation. Goes from -infinity to 3. And I guess the European interval notation, -infinity, because you never know when you're going to go to Europe. You never know when you're going to go to Europe and use interval notation. Hey, you never know. Just like you never know when you're going to use vosotros and go to Spain, right? Which actually happened, because I went to Spain. I didn't use vosotros, but Gary did. Okay, so there you go. Good job, guys. Next one, number 5. Once again, I'm going to take that radicand, 2 minus domain equals 2 minus x has to be greater than or equal to 0. -x is greater than or equal to -2. U-turn. Okay. Let me just check my work. 2. Okay. Let's go ahead and write that in step builder notation. X such that x is less than or equal to 2. Domain is going to be -infinity to 2. 2 is going to be the highest number for the domain. Let's go ahead and write it European way. -2. As for the range, change the color. The range. Oh, I forgot to make my background black. Oh man, I forgot. Go ahead and make my background black. Now better. Yes. I like it black. The colors stand out more. Okay, the range. Now remember, for the range, that just the radicand itself, 2 minus x, has to be greater than or equal to 0. And then we have to multiply by a -3. -3 times. And what you do to one side, you have to do to the other. When you multiply, remember, you turn, and that becomes a 0. And then you're going to add 1 to it. So we're going to add 1 minus 3, 2 minus x less than or equal to 0 plus 1. So therefore, this implies that y is going to be less than or equal to 1. If I rewrite that as a range, y is going to be less than or equal to 1. The range, we have a -infinity to 1, and the range is going to be -infinity to 1. Okay? Good job, guys. Good job. Next one. Okay. Once again, another radical. Take that radicand for the domain. Set it greater than or equal to 0. And then we have x is greater than or equal to 1. Write the domain in set builder notation. X is greater than or equal to 1. Let's go ahead and rewrite it in set builder notation. Starts at 1, goes to positive infinity. The other set builder notation, 1, positive infinity. Now let's look at the range. Blue. Let's look at the range. We had the entire radical, x minus 1, has to be greater than or equal to 0. Now we multiply by a -2. You have to multiply both sides. Greater than or equal to. Whoops. U-turn. 0 times -2. So therefore, the y has to be less than or equal to -2. Range y such that y is less than or equal to -2. Range -infinity to -2. And then range, we can do one of these businesses, -2. There you go. Good job, guys. Now we're heading into the big boys. Big boys and big girls. Okay, so we're on to these rational functions that gave us some difficulty. And I think even in class when I was doing the problem, we didn't really define the true range of them. And so that's why I went back and so let's go ahead and find the domain. Now the domain of rational functions is restricted by the denominator, okay? So x squared minus 3x equals 0. And you guys get confused with equals 0 and doesn't equal 0, okay? Equal 0 is an equation. It's an actual equation. You solve it. Equations are used for solving. Okay. Doesn't equal 0 is information only. It's just information. It's just plainly stated that x doesn't equal that number. So when you're solving an equation, you have to write it equal to. And when you're defining an asymptote, it has to be equal to. When you are restricting the domain, it has to be not equal to. Okay? So once again, we're solving this equation. Let's go ahead and factor. X minus 3 equals 0. This implies, okay, something just happened. This implies, so we have x equals 0. This implies that x equals 0 and x equals 3. Okay, so those are my two vertical asymptotes. So my vertical asymptotes were x equals 0 and x equals 3. If these two, and I mean, I could be a very stickler for these kinds of things because it is very important that you use the math language properly. If on the quiz or test, if you said x does not equal, what are you telling me? That vertical asymptotes don't equal those things? They have to be equal to. They have to be a vertical line. Okay, now let's go ahead and write the domain for it. All set of x such that x cannot be equal to 0 and x cannot be equal to 3. So notice the difference where I wrote the not equal to and equal to. This is telling me, hey, here are the asymptotes. This right here is a description of the x's for this function. So while these asymptotes are excluded from the description of what x could be for this function, the vertical asymptotes of these functions equal 0 and 3. Okay? I hope that makes sense. Okay, now the range is also going to be, because this cannot be 0, that 4 is not 0. So it has to be y equals 0. That is the horizontal asymptote. Horizontal asymptote. And so I looked in all over. I have several pre-calculus books at my house. And in most cases, they don't ask you to write the range of rational functions because it couldn't be difficult. But I mean, we are North Hills, so I'm going to ask you to find the range. And so we have to kind of draw a rinky-dink little sketch, rough sketch of this graph. So what I'm going to do is in here, I'm going to include all of my asymptotes. There's my x equals 0, and 1, 2, 3. There is my x equals 3. And right there is my y equals 0. And inside of there, I'm going to test points of x points to see and put it back into this equation to see where the y points will occur. Okay, will it be above or below that y equals 0? So when I put in a number that is left of x equals 0, x equals -1, I'm just focusing on the sign. Put it back in. Let's go ahead. Kind of, can I zoom a little bit more? I've put it in, it becomes 4, and we have a negative times a positive, and a negative times a positive times a positive. So it's going to be somewhere here, being trapped by those two. I'm going to put it in a different color. It's going to be a positive number, being trapped in between this asymptote and that asymptote. Now, let's go ahead and put a number that is greater than 3. So x equals like 4. When I put that in, it's going to be 4 over 4 times 4 is positive, and that's going to become a, let's see, 4, 16, and then, 4, 16, I actually have to do it, 16 minus 3 times 12, that's going to be a positive, okay? So it's going to be a positive, and once again, that graph, what's going to be a positive? The y value is going to be a positive, okay, because these equal y. Now, there's that little u bit in the middle. And I know this because I just know rational functions. I don't really, yes, I know them, but I don't know them, okay? Do you know your rational functions? Okay, so let's pick a number. So like x equals 1 in between 0 and 3. So when I put that in, 1 over, that's going to be positive 1 squared, and then it's going to be a negative. It's going to be down here, okay? So what I have to look is that rational functions are usually symmetric. And if you look, here is the asymptote x equals 0. Here is the asymptote x equals 3. And this u bit in here has to be trapped between those asymptotes. And so what I'm trying to find is kind of like the vertex. And that vertex is going to occur in the half point between 0 and 3. The halfway point between 0 and 3 is 1.5 or 3 halves. Okay, so let's go ahead and put x equals 3 halves back into the function. And I get 4 over 3 halves squared minus 3 times 3 halves. So we have 4 over, it's 9 fourths minus 9 halves. And then we have 4 over, 9 minus 18 over 4. And then that is 4 over negative 9 over 4. So this, I'm going to write it this way, is 4 times 4 over negative 9. So that's negative 16 over negative 9. So this value right here, where's my mouse cursor? This point right here is going to be, what is these, all these negatives right here? Oh, I just erased it. Negative 16 over 9. Okay, that little point right there is going to have an x value. Ah, it's so messy. Ah. Okay, that little point is going to have an x value. What did we set as an x value right here? And that's the y value right there. So it's going to be 3 halves and negative 16 over 9. So now we can determine our range. Okay, how do we determine our range? Our range is now going to be positive, or I'm going to start down here. It's going to be negative infinity. It's going to start at negative infinity. Right here, negative infinity, all the way down here. All the way down there. And then it stops at negative 16 over 9. But it includes negative 16 over 9. And then it jumps up to where this asymptote is. Both of these graphs right here are going to get closer and closer to 0, but don't touch it. Later on, you're going to figure out those are limits. It's very important that you understand asymptotes because that's where we're leading to calculus. Okay, so it's going to get closer and closer to 0, and then it's going to go up to positive infinity. So to represent that, the range is going to be y such that, let's go ahead and y is less than or equal to negative 16 over 9, or y is greater than 0. So here is, let's go ahead and make this a little bit prettier. Do it in a different color. So the asymptotes for that function was x equals 0, x equals 3, and y equals 0. And then the domain was x such that x cannot be 0, x cannot be 3, and then range is y such that y is less than or equal to negative 16/9, or y is greater than 0. Okay, if I put this as interval notation, it is going to be negative infinity to 0, doesn't include 0, and then it is going to be 0, 3, and 3 to positive infinity. For the range, it is going to be negative infinity to negative 16/9, and then it starts at 0 and goes to positive infinity. Notice that it doesn't have that bit in the middle. Okay, this little bit right here, to further colorify my graph. It won't let me zoom in. Oh, now it will. This little bit between, it's not letting me highlight. Okay, this little bit between 0, this right here, and negative 16/9. Okay, wow, that's a lot of work for one little problem. Don't you love it? Okay, let's do the next one. So we have to find the domain and range and the asymptotes. Let's go ahead and find all of its asymptotes, because asymptotes are pretty straightforward. For the domain, for the vertical asymptote, write this, take that denominator, set it equal to 0, x plus 3, x minus 3 equals 0. So x equals plus or minus 3. And this is the only time you can write that equation as plus or minus, because that's actually a math symbol. That plus or minus is an actual math symbol. So the asymptotes are x equals plus or minus 3. Okay? And then let's go ahead and find the horizontal asymptote. Horizontal asymptote, since that can't be 0, is y equals 0. And y equals 0. Now, from this vertical asymptote, I can say, therefore, the domain equals x such that x cannot be plus or minus 3. Okay, so my domain is going to be, shouldn't put colons, we'll get in trouble, x such that x cannot be plus or minus 3. If I put it in interval notation, that will be negative infinity. It goes to negative 3. That's the first one it's going to hit on that number line, and then goes to negative 3 and 3, and then 3 and positive infinity. Okay, now let's look at the horizontal asymptote. Horizontal asymptote is y equals 0. Now let's go ahead and define the range. Let's go ahead and draw a sketch of the graph and include all of the asymptotes. So we have this asymptote right here. It's the horizontal asymptote. And we had 1, 2, 3. It's a vertical asymptote. negative 1, 2, 3, and that's the other. So this was x equals 3, and this was x equals negative 3. Let's go ahead and find a number that's less than negative 3, negative 4. And then I'm going to find that I'm going to get a 1 over, it's a positive, and then positive 16. 16 is still bigger than 9, so that's going to be a positive. So it's going to happen right here. Okay? Now, x equals 3, x equals 4 is bigger, so that is going to be 16 once again, and it's going to be a positive. Something like that. I'm not happy with my just like that. So we're going to have a U business. We're probably going to have it below 0 from what I see. So I can put it x equals 0 to test it. And that just happens to be smack dab right in the middle of 3 and negative 3. Okay, and so I'm going to go ahead and actually figure out what that is. F of 0 equals 1 over 0, 1. So that's f of 0 equals negative 1/9. That is going to tell me my maximum point of that middle bit right here. And it's probably going to go down like this. So this area between 0 and negative 1/9 is not going to be used by the range. Okay, but it also includes negative 1/9. So let's go ahead and define my range. Range y such that, y such that y has to be less than or equal to negative 1/9, or y has to be greater than 0. So the range, if I write it in terminal notation, is going to be negative infinity to negative 1/9. Close my bracket. It excludes this area right here, starts again at 0, but doesn't include 0 and goes to positive infinity. Okay? Good job, guys. Next one. Okay, let's go ahead and determine all of the asymptotes. All of the asymptotes. So let's go ahead and take, for the vertical asymptote, set that denominator equal to 0, factor x plus and minus, so it's going to be 3 and 1, okay, and then x equals negative 3, x equals 1. So we have x equals negative 3, x equals 1. The numerator is a constant, so my asymptote, horizontal asymptote, is going to be y equals 0. Based on these vertical asymptotes, I can define my domain. Domain x such that x cannot be negative 3, x cannot be 1. Rewrite it. I need to stop putting colons. So we have negative infinity, gets close to negative 3 but doesn't touch it, starts over at negative 3, doesn't touch it, gets close to 1, doesn't touch it, starts at 1, doesn't touch it, and goes to positive infinity. Okay, now let's draw a graph, and let's put all of our asymptotes. Here is y equals 0. And we have 1, 2, 3. Oops. There's our -3. And then we have 1. Y equals 1. And then put in a number that is less than -3. Pink. No. Green. X equals -4. Let's put that back in there. So we have a negative and then 1 over -16, 16, minus 8 minus 3. So it's going to be what? 16 and minus 8, 11. That's going to be a positive, but it's going to be a negative because of that negative down here. Trap it. And then let's pick a number greater. So x equals 2. And then we have a -1. And that's 4 plus 4 minus 3. Oh, wow. What am I doing here? I looked at this. This is wrong. So we have 16. No, that's right. Minus 8. It's a -11. 16. Okay. So it's that. And then this is a positive. And then it becomes a negative because of this right here. So my y value is going to be negative. Right there. Okay, the halfway point between -3 and 1, okay? Halfway point between -3 and 1 is going to be, what is that, 4 divided by 2. Sorry, my mom came by the door, dropped off some soup. So the halfway point is going to be -1, I think. Okay, so let's go ahead and put that in. X equals -1, negative over -1 squared plus 2, -1 minus 3. That's 1 minus 2 minus 3. 1 minus 5. That's -4. Negative and a negative is a positive. So positive 1 over 4. Okay, so that is going to be somewhere right there. There's my parabola looking thing. Okay, and this is going to be my y value. Let's go ahead using that information. Notice once again this little area between 0 and 1/4 doesn't get used. So the range is going to be y such that y has to be less than 0, has to be less than 0, or y has to be greater than or equal to 1/4. If I rewrite that in interval notation, it's going to be -infinity to 0. Gets closer and closer to 0, but doesn't touch it right here. And then it jumps over to 1/4, and positive infinity. Okay? Good job, guys. Good job. Okay, next one. Let's go ahead and define our asymptotes. And once again, the numerator is a constant, so it's going to be y equals 0. And we have set the denominator equal to 0. So it's going to be x plus 2, and x plus 2 equals 0. So that's going to be x equals -2. Okay, and then I can go ahead and define my domain based on my one vertical asymptote. So x and x cannot be -2. If I rewrite that in interval notation, -infinity, -2, -2, +infinity. This one only has one vertical asymptote. Okay, let's go ahead and draw that graph. This one do. Oh, okay. And then here is y equals 0, horizontal asymptote, and -2. 1, 2, asymptote. X equals -2. Let's go ahead and put in a number. X equals -3, that's less than -2. 2, and then that is a -1 squared, and it's going to be a positive. So it's going to look something like this. Right? And then let's put in a 0. Okay, x equals 0, and that's going to be still a positive, so it's going to end up looking like this. So for this function, since we only have one vertical asymptote, okay, we can't get that little business in the middle, that little u business in the middle, okay? So this kind of looks like just a regular, you know, it kind of looks like this. We have the left and right side with these kind of graphs, and it's missing this. So it took this asymptote and kind of sandwiched it with this, and so it's missing that u business, but it still has these two graphs on the same side of the horizontal asymptote, whereas a traditional rational function would split it up kind of like this. Okay, and so that's the way it looks. So we really didn't need to go any further in, but it's always nice to have a little graph of it. Why is that? And this is y is greater than 0, right? Y is greater than 0. For a traditional function, the range would just exclude the horizontal asymptote, because we can have all these numbers down here and all these numbers down here. But this has a quadratic in the numerator, but because the quadratic is a perfect square trinomial and it factors as the same x value, it kind of takes this graph and kind of reflects it over the x-axis. Okay, if I write this as a range, it's going to start at 0 and go to positive. That one was easy, yes. Okay, good job, guys. Okay, we're almost there. Okay, we've got like 4 more if you're watching the entire video. Let's go ahead and write the asymptote. Uh-huh. 2x squared plus 9x minus 18 equals 0. Let's go ahead and factor. And looking at the NYP math book that I have, because I really didn't look at it until just recently, and while I was making that, the problem was for 8A to do while I was going to be gone that only one day. There was another way, to factor that it showed, which is a brand new way of factoring. It may be difficult for some of you guys. It was difficult for me, and it was splitting this 9x into two terms. So if I take this, and it'll be an x, and this will be made up of another x and minus 18 equals 0. And to split it up, so when we group them later, we have common factors, binomial factors. Okay, so for example, okay, well, I have to actually figure this out. This was the hardest method for me, but for some people, I mean, addition just makes sense to them and they see patterns. So this might be like an easier method for you. And you can always do A times C. And then when you multiply, you have to, at the end, you have to do the opposite and divide by 2. That was the AC method. But up to you. So let me just show you quickly how that new method is done. If you want to use it, you can. So basically, we're splitting up the two terms. And for this one, we would have to make it negative. That term would have to be negative. So we have to figure out two numbers. When you subtract and find the difference, you get 9. So we could try like 12 and 3. Okay, that middle term will give you 9. But when I group the first two, I can factor out a 2x, and it's x plus 6. And then for this, I'm going to factor out a 3, negative 3. And it's important that it's a negative, so that's x, and then plus 6. And if you remember factoring by grouping, you can take out an x plus 6, and that becomes 2x minus 3. So breaking that middle term up, and basically, this is what you see when you do FOIL. Remember FOIL on these two binomials. And so breaking that up, that middle term could kind of, that's another method. Maybe I'll make a video on all the different factoring methods, factoring trinomials. Okay, so, and I think I have videos in my YouTube channel. There's a whole bunch of videos about factoring trinomials, so you might want to search and look for those. This is a brand new method, but I usually do trial and error x, and then, but I already know it, so it's minus, plus I'm going to cheat a little bit, 6 and 3. Okay, so that's, oh no, wait a second. That doesn't work. Oh, yes it does. Okay, 2, 2, negative 18, and then negative 3, and positive 12. Okay, and then let's see, x equals 3/2, and x equals negative 6. So the asymptotes are x equals 3/2, and x equals negative 6. Okay, my horizontal asymptote is going to be y equals 0 because that numerator is a constant. Okay, now let's go ahead and figure out the domain. So x and x cannot be equal to 3/2 and negative 6. And then if I rewrite that in interval notation, it'll be negative infinity, reaches negative 6 first, gets close to it, starts at negative 6, doesn't touch negative 6, gets to 3/2, but doesn't touch 3/2, starts at 3/2, doesn't touch 3/2, and gets to positive infinity. Okay, let's go ahead and draw our little graph. And put all of our asymptotes on it. It's equals 0, and 1, 2, 3, 4, 5, 6. X equals negative 6, and then 3, 1, 2, 1.5, which is going to be right there. Y equals 3/2, 1.5. Okay, and to figure out, and if you can skip ahead, you can if you want to. To figure out that middle point, I'm going to use the distance formula. 6 plus 1.5 divided by 2, which is 7.5 divided by 2. which is 3 point, whoa, oh, gosh, 3.157, and then 5. Is that right? .75 times 2, 7.5. Yep. Okay. So that'll be my x. Nope, that's not going to be my x. Now I have to count. Okay. So we started at 1.5. I'm going to go left. So 1.5 minus 3.75. 1.5 minus 3.75 equals negative 2.25, which is negative 2 1/4. Negative 2 1/4, which is negative 9/4. Negative 9/4. This is why you need to know your midpoint. As I was saying, this is why you need to know your midpoint formula. Or just know how to find the middle point between two numbers. Okay, so that was your x, right? Let's go ahead and put that in. X equals negative 9/4. Negative 1 over 2 times negative 9/4 squared plus 9 times negative 9/4 minus 18. So we have negative 1 and 2 times 81/16 minus 81/4 minus 18. Just going to use my calculator. Put in negative 9 divided by 4. Enter, store it as x. Enter, put in that whole negative 1 divided by 2x squared. X squared plus 9x plus 9x minus 18. And then go to math. Where is that? Into fractions. 8/225. Is that right? Or y equals negative 8/225. Yep, I think that's right. Okay, and then so that's my y value, and my range is now going to be, I can graph that if I wanted to. It's going to look like this. It's going to look like this. Is it a negative? No, it was a positive. Whoops. Sorry. It's taking a really long time to do this one problem. It's going to look like this. It's going to be like that. And then, so that's going to be a positive 800, which is 0.0036. So it's going to be very close. Negative 2, 1, 2, somewhere here. Oh, bam, bam, bam. Okay, so the range is going to be y, such that y has to be less than 0 or y has to be greater than or equal to 8 over 225. Range, so that is going to start at negative infinity, and then it's going to stop at 0, but doesn't touch 0. It's going to start back at up 8 over 225 to positive infinity. Okay? Good job. That took forever. Okay. Now we have a double whammy. We have a radical and we have a rational. So for these problems, figuring out where to get your asymptotes and where to get the domain and range is important. So the asymptotes are going to come from the rational function part of the equation. Okay, domain and range, because it's more restrictive. It's more not, I don't want to say restrictive, but it has to be include all of the elements that make up the x values and the y values. That's going to come from the radical function. Okay, so let's go ahead and find the asymptotes. Let's go ahead and find the asymptotes. So first, look at the denominator. 3x plus 6. Because it's a rational, this cannot be equal to 0. Or you can get the vertical asymptote by setting it equal to 0. So this implies that x equals -2. Okay, that's your asymptote. X equals -2. And if you look, the numerator is a constant, which tells us if I just treat this like a pure rational function, the horizontal asymptote is going to be y equals 0. Okay, now let's go ahead and figure out the domain. Now, the domain of this function is going to be affected by the fact that it is a radical. Okay, the entire denominator, okay, has a radical sign with it. So I have to figure out 3x plus 0, and that has to be greater than or equal to 0. Okay. Now, it can't equal 0. What happens if it equals 0? If I have the square root of 0 in the denominator, that also makes it undefined. So we know that it has to be greater than 0. Okay. So let's go ahead and solve it. We already did. So x has to be greater than -2. Let's go ahead and test that. Well, I don't really have to test it. There's only one. So the domain of this is going to be, so it's x has to be greater than -2. And so it starts at -2, oh, whoops. Starts at -2 and goes to positive infinity. Okay. Now, the range. The range is going to be determined by the square root of 3x plus 6. Okay, and that has to be greater than or equal to 0. Okay, but once again, it can't equal 0. So the whole function has to be greater than 0. So the range y such that y has to be greater than 0. Right? And so it starts at 0 and goes to positive infinity. Okay? You can graph it if you want. Start a new one. So y equals 2 divided by square root of 3x plus 6 it starts right here at, looks like negative 2. Let me trace that. Starts at negative 2. Okay. And then notice the y is never ever going to get, nope. You see the table. Negative 2, there's an error, right? Because there's an asymptote there. And then you can continue and look at the y's. You can keep on going and keep on going. Keep on going. I could do this forever. It's never going to get to 0. Okay? Good job. Next one. 2 more. Now remember, I told you this is a triple whammy. This is a rational where the asymptotes are going to come from. And this is a radical, which is where the domain and range are going to come from. But it's also a quadratic in the denominator. Well, the radicand is a quadratic. So you have to test the domains. So let's look at the rational portion. I can disregard, whoops, the radical sign. 2x squared minus 3x minus 2, set it equal to 0. 2x plus x minus, it's going to be a 2, 1, yep, so x equals negative 1/2, x equals 2. There are my 2 asymptotes. X equals negative 1/2, x equals 2. The numerator is a constant, so there is my other asymptote. Okay, now to define the domain, I have to take the entire radical and set it greater than or equal to 0. But once again, it can't be equal to 0, just greater than 0. So square both sides. We have 2x squared minus 3x minus 2 greater than 0. We've already factored that. So 2x plus 1, x minus 2. So here we have our test points. Okay, I made you test these points on a number line. Negative 1/2 and 2. One of the things that you should be able to recognize is that greater than Is it greater than? It means that it's going to be the outer two intervals right here. Okay. When you multiply those two, it's going to be the parts that are greater than. This right here, I could test a point here, x equals 0. We have a positive and multiply by a negative, right? And I'm just putting that 0 back into the to right here, to those two factors. Okay, and that is not greater than 0. A negative number is not greater than 0, so that middle area is not going to work. And so usually when you have a situation like this, if it's greater than, then it's going to be an or. It's going to be the two outer. When it's less than, it's going to be the union of the two factors. Okay, so it's going to be in the middle. So now I can state my domain. My domain is going to be negative, x such that x has to be less than negative 1/2, or x has to be greater than 2. If I rewrite that in interval notation, negative infinity to negative 1/2 does not include 1/2, starts at 2 and goes to positive infinity. Now the range of this, the range once again is going to be defined by the radical. This right here, the entire function has to be greater than 0. So y has to be greater than 0. So y such that y has to be greater than 0. The range is going to be starting at 0 and goes to positive infinity. Okay? Good job. Last one, yay. Once again, we have this problem going on right here. And so let's go ahead and figure out the asymptotes. Y equals 0, because that numerator is a constant of 2. And then we can get 4x squared minus 25 equal to 0. 2x plus 2x minus, difference of squares. So x equals negative 5/2 plus or minus 5/2. X equals plus or minus 5/2. Okay, now let's go ahead and create our boundaries. So we have negative 5/2 and 5/2. And remember, we're trying to figure this out. 5 has to be greater than 0. And so that's 2x plus 5. 2x minus 5 has to be greater than 0. And once again, once that greater than 0 will tell you that x has to be those outer intersections. Okay? So your domain is going to be x such that x has to be less than negative 5/2, or x has to be greater than 5/2. If I rewrite that in interval notation, negative 5/2, and I'm going to run out of room. Domain. It's going to be negative infinity to negative 5/2, 5/2, positive infinity. My range, remember the entire function, this entire function. So if I take 4x squared minus 25, and that has to be greater than 0, Okay, but it's being multiplied by -1. So -1 times 4x squared minus 25. When I multiply by a negative, it's a U-turn. So once again, that inequality sign is going to do a U-turn. So my range for this, and this is the y. Y such that y has to be less than 0. If I rewrite it, that is going to be -infinity to 0. Okay. Good job, guys. That was 1 hour and 15 minutes of fun. Yes. Bye.